Welcome back everyone. So let us continue this discussion which we were having in the last class on the directional derivatives and the direction in which they increase or decrease the fastest or increase or decrease the most rapidly. Okay, so we had seen that the directional derivative increases the most rapidly in the direction when the unit vector is given by gradient of f divided by norm of the gradient. Okay, so basically the unit vector in the direction of the gradient. Same way, it will decrease the most when you have negative of the gradient. Okay, just convert it to a unit vector, and uh, yeah, and this is the directional derivative is 0. Okay, when that gradient of f and u are orthogonal. Okay, that's basically given by this vector u, which is plus or minus fy fx divided by the gradient of f. Okay, yeah. So basically, now just write over there that this is the direction of no change. Okay. Direction of no change. Okay. Change. No change in f. Okay. In f. No change in f. Okay. So, anyways, we'll see one example based on this three statements of mine. Okay. So, consider the example. Consider f from 2 to r given by f of x y is equal to 6 minus x cube minus y square. Okay. So, having considered this, let us calculate the gradient first. So, what is going to be for the gradient? We require the partial derivative. So, fx at xy, this is going to become minus 3x square and fy okay. So, we'll consider a simple point. We'll take 1 only, so this point values come nice. Fx at 1 1. Okay, this is my x naught y naught in this case. Okay, yeah, so this is going to become minus 3 fy of xy is equal to minus 2. Okay. Fy of xy is equal to minus 2. Okay. So the gradient of f at 1 comma 1, this will be equal to minus 3 minus 2. Okay. Now to do our further arguments, we require modulus of this, means the norm of this. Okay, that's going to give me norm of minus 3 minus 2. This is going to become root over 9 plus 4, that is root 13. Okay. So hence the steepest ascent, means the direction in which it's increasing the most rapidly, the steepest ascent is in the direction gradient of f 1 comma 1, okay, divided by norm of gradient of 1 comma 1. Okay, this is going to be minus 3 by root 13 and minus 2 by root 13. Okay, we'll write 1 now. 2, the steepest descent, the direction in which it's decreasing the most rapidly, wait, what am I talking? Just to mention what I'm talking about. No? This is the steepest ascent just a moment. Steepest ascent of the surface z is equal to fxy. Okay, the surface where z is equal to fxy, where fxy is the function above. So basically you have a surface here in 3 dimensions. Okay, basically the graph of this function is a surface, like how graph of your one variable functions were curves in the 2-dimensional space. Graphs of a 2-dimensional function becomes a surface in the 3-dimensional space. Okay, so sorry, this is 6 minus x cube minus y square. Okay, so if you plot this surface is increasing at the point 1 comma 1. The surface is rising the fastest in this direction and it will decreasing the fastest in this direction, which I'm going to write now. Okay, the steepest descent okay, d, yes it is, descent is in the direction steepest descent again of z is equal to fxy. Okay, we won't say surface amount, let it be understood. Okay, is in the direction given by minus gradient of f Okay, steepest descent is in the direction of y square. This 3 by root 13 and 2 by root 13. Okay, and then next, the direction of no change. Direction the directions we're getting two directions, because of plus and minus sign. The directions of no change, are plus or minus fy first. So one second, let me write down the formula. fy11 minus fx11 upon gradient of f at 11 so this will leave me with plus or minus two directions, because this is plus and one is minus. So I'm using the word the directions. Sorry, I forgot to write this. This is plural over here. Directions. Okay. Because there are two directions here. Okay, so this will become 2 by root 13. Okay, and then this will be minus 3 by root 13 over here. Okay, I've written the norm of f, gradient of f inside already. I don't have to divide anything. Okay, so that's about this example over here. Okay, so now let us move back to the result which we are focusing on, main result. So what did the main result say? If a function f is let d be a subset of R2, let x0 y0 be an interior point of d. If a f d to R is differentiable at x0 y0, then for every unit vector u is equal to u1 u2 in R2, the directional derivatives du f of x0 y0 exist, and moreover the directional derivative can be written as a product of the gradient into the unit vector. Okay, so if a function is differentiable, then the directional derivative exists, and more importantly this property is satisfied. Okay, so try to recall that earlier on when we had done examples on directional derivatives, okay, we had seen that some functions do not satisfy this particular property. Okay, this particular property which I have said here, there are some functions which don't satisfy this property. Please go and check your examples on directional derivatives. So now we know that those functions who are not satisfying this property, they are not going to be differentiable. Okay, so if a function does not satisfy this property, it will not be differentiable, because if it is differentiable, then it should satisfy this property. Okay, secondly, if the directional derivative of a function does not exist in any direction, because we said if it's differentiable, then in every unit vector direction the directional derivative will exist. But if it is not existing in some direction, that means the function is not differentiable at that point. Okay, so we have two conditions over here to check the differentiability of a given function. Okay, so it's basically using the contrapositive of the statement. So if it is if the directional derivative does not exist in any direction, then a function will not be differentiable. And sometimes the directional derivative may exist in all directions, but this property in the green box, this is not satisfied. Okay, and that will also imply that a function is not differentiable. Okay, Let us see some examples based on this what I just said. Yeah, so let examples examples 1, let f r2 let f from r2 to r be given by be given by root over this step. Okay, okay, so we have already seen that. Recall what we have seen so far. We have done this function earlier on. If you can't find it, no problem, we can just redo these things. F is continuous, at 0 comma 0. Okay, the partial derivatives exist at 0 comma 0. Okay, and both are 0. Okay, just use the definition over here, you will get the answer 0 in one step. Okay, okay, so next let us try to find the directional derivatives. Okay, consider any unit vector in R2. R2. Then for t belong to R, t not equal to 0, consider this ratio consider this ratio f of basically this is the formula for directional derivatives. Okay, this is nothing but the formula of the directional derivatives. If I take limit t tending to 0, I'll get the directional derivative. Let me simplify this expression. That's why I wrote it like this. Okay, and what will this be? Here we'll be getting t square u1 u2, okay, minus 0 upon t. Okay, so simplifying it little more, This will leave me with modulo of t square. I'll take out, it will become modulus of t. Okay, divide by t. Okay, so this is what you get here. Now try to recall what you have done in the basic real analysis. But this limit, see, u1 u2 is constant, so ignore this square root part. What we have to focus on is only on this limit of this quantity as t tends to 0. Okay, but what do you know about limit of t tending to 0 of this quantity? What happens here? Just a reminder, in case I forgot, this is, if you tend to 0 in the positive direction, this quantity becomes limit of t tending to 0 in the positive direction. Now if t is greater than 0, that is the positive direction of 0, in that case modulus of t is equal to t. Right, since we are tending towards 0 from the right hand side, okay, t is greater than 0, okay, and hence modulus of t is going to be equal to t, and this is going to be, this limit value will come equal to 1. Okay, same way if you are tending towards 0 in the negative direction, okay, at the left hand side of 0, that time this is going to become limit of uh, your modulus of t will become minus of t, right, when t is less than 0, right. So this will cancel out and give you minus 1. So what do you know? Hence limit does not exist. Okay, so you know that this limit does not exist. Okay, so what can you say about the directional derivative over here? Okay, so this limit over here will not exist once you take limit t tending to 0, right? So it won't exist. So the directional derivative does not exist in any direction over here at 0 comma 0, because I taken u to be arbitrary in some specific direction. Hence directional derivative du f at 0 comma 0 doesn't exist for any direction. Any direction at 0 comma 0. Okay, hence f is not differentiable at 0 comma 0. Okay, f is not differentiable at 0 comma 0. Okay, okay. So moving on to the next example. So if we saw that in this example the function is not differentiable, hence it didn't have directional derivative, so it's not differentiable. Okay, so let's go to the next example here. So the next example will be f from R2 to R, f from R2 to R given by given by f of xy xy oh, it's going to be equal to x square y upon x square y square and 0. This is when x square y is not equal to 0 comma 0. Yeah, xy is not equal to 0 comma 0. This is xy is equal to 0 comma 0. This formula is not valid when xy is 0 comma 0, so you have to define it separately at 0 comma 0. Okay, so this is the so this is a function f is continuous at 0 comma 0. Okay, this will require a proof. I'm not 100% sure if you have done this example, but I'll just briefly explain what is to be done. You have to put x is equal to r cos theta, right? Y is equal to r sin theta. R sin theta. Okay, so this will leave you with f of xy. This leaves you with r cube. This leaves you with r cube cos square theta sin theta, and denominator will become r square cos square theta plus r square sin square theta. we take r square common here and cancel out the numerator term. Denominator will become 1. So what remains here is only r cos square theta and sin theta. Okay. Now notice here, claim is that I have to show that modulus of f of xy minus f of 0 0 are less than epsilon, right? So basically this is what I want to show. So just consider this. I want to show it's less than epsilon, no? So let me calculate this quantity first. Okay, so this is going to be equal to r cos square theta sin theta Okay, so this becomes modulus of r into modulus of cos square theta and modulus of sin theta. So this will become less equal to r because these two quantities are less than 1. So this will be less than r. So you have to choose your r small enough such that this will become less than epsilon. Okay, so basically this is your this quantity is nothing but your root over x square plus y square, right? Root over x square plus y square. So in this case, right, so you want this quantity to be less than epsilon. Right, so we want root over x square plus y square to be less than epsilon, and hence all these things will be true, right? In other words, you want to find a delta such that this happens. Okay, so now okay, so how do we proceed from here? So we want this to happen, right? So now we'll work this out on rough. Rough work, what I'm writing in yellow. So if we want this to happen less than epsilon, then this will happen. This will imply that this is true, right? So what we do is we let, now it's very essential here that you write let over here, not implies. So let x square by 2, x square be less than epsilon square by 2, right, and y square be less than epsilon square by 2. Okay, this is not a direct follow up from the statement. I am assuming this condition that x square is less than epsilon square by 2 and y square is less than epsilon square by 2. Okay, if you add two numbers, you will addition of two numbers is not equal to half of their sum. Okay, So we are assuming this statement over here. Keep that in mind. If this is true, then this above statement is true. But if the above statement is true, the down one is not. Okay. So this one, for the sake of simplicity, we are assuming the down statement is true. Okay. So if this happens, we'll be getting take square root now. This will imply that x can be positive or negative, right? So when we're taking square root, we'll have to take the write the modulus over there. Epsilon was we started off with positive epsilon in the problem. So the square root is going to give you positive epsilon only. Same about root 2. Here also same thing. Okay, is less than epsilon by root 2. So that is what have we written here. X minus 0 is less than epsilon by root 2. Okay, and y minus 0 is less than epsilon by root 2. Okay. So okay, so this is true. So now choose delta is equal to epsilon by root 2. Clearly it is greater than 0. Okay, so when mod x minus 0 modulus of x minus 0 is less than delta and y minus 0 is less than delta, what you will be getting? This will imply that this will imply that uh, mod x is less than delta and mod y is less than delta. This implies that x square is less than delta square and y square is less than delta square. So x square plus y square, okay, is going to be less than directly, add it up here. This is going to be less than 2 delta square, which is going to be delta square is going to be epsilon square by 2. So 2 and 2 will cancel. Okay, so this is epsilon square by 2, multiplying another 2 there. So we'll get x square plus y square less than epsilon square. Okay, so taking square root on both sides, we'll be left with root over x square plus y square is less equal to epsilon, but this is equal to r. So modulus of r is less than this thing, epsilon. So but we know that f of xy was less than r. Okay, so hence we know that f of xy is over here. Okay, I made this thing. This was the fair part of the problem. I hope you all didn't write with yellow part. Okay, this was the end of rough work here. End of rough work. Now this is the fair part of the problem. Sorry, I forgot about that. Yeah. So f of xy is less than epsilon over here. Okay, hence when x minus 0 is less than epsilon by root 2 and y minus 0 is less than epsilon by root 2, we get f of xy, and this is modulus of f of xy minus f of 0 0, that is 0. Okay, this is equal to modulus of f of xy. Okay, this is less than epsilon. Okay, hence f is continuous over there. Hence f is continuous at 0 comma 0. Okay, so we have shown that f is continuous at 0 comma 0. Yeah, so the continuity condition I have satisfied. Yeah, why am I showing continuity, by the way? Yeah, so there is one theorem which I'm proving next. I should have done this theorem prior to this video. This theorem says that if a function is continuous and one of the partial derivatives exists over there, okay, no, we're not referring to that theorem, sorry. No. Anyways, we're just checking if the function is continuous, because if the function is discontinuous, then there's no point in talking of derivatives over there. Okay, that's based on the previous result which we had done prior to this already. Okay, so if you have a discontinuous function, there's no point in talking of its derivative at the point. Okay, so let's move on now to the next thing, that is finding the partial derivatives. Okay, well, instead of finding the partial derivatives now, I'll find the directional derivative straight away, and then I'll put the particular directional values. Okay, so consider u is equal to u1 u2 a unit vector in n unit vector. N unit vector in R2 n unit vector in R2. Okay, so for t belonging to R, t not equal to 0, okay, what is going to be this ratio? F of 0 plus tu1 0 plus tu2 minus f of 0 comma 0 upon t. This ratio is going to become f of tu1 tu2 minus 0 f of 0 0 0 upon t. So this is equal to t square u1 square, okay, into t u1 t u2, okay, upon t square u1 square plus t square u2 square. Okay, and this whole expression divided by t. So as you can see, numerator becomes t cube u1 square u2 upon the denominator. T square comes out common and one more t comes here, so this is also t cube into u1 square plus u2 square, right? They cancel out and they leave you with u1 square u2 upon u1 square u2 square. Okay, so if I take limit t tending to 0 in the above expression, take limit t tending to 0, what are we going to get? The LHS becomes du directional derivative at 0 0 and the RHS is the silly. Okay, okay, so these are the directional derivatives of yours. So all the directional derivatives exist. Okay, derivatives exist. Okay, okay, in particular in particular uh, in particular the directional derivative along x, let's say partial derivative with respect to x at 0 comma 0, what will this be? Here what you do, this is nothing but d of 1 comma 0, so you take u1 as 1 and u2 as 0, so this leaves you with this as 0. Same way, okay, page is over. Same way, your partial derivative with respect to y is nothing but directional derivative along 0 comma 1 at 0 comma 0, this leaves you with 0 comma 1 0 0, this leaves you with 0, this leaves you with yeah, numerator will be 0, denominator is 1, this is also 0. Okay, so now the problem over here is everything appears to be fine, but what is going to be the gradient of f at 0 comma 0? This is nothing but fx at 0 comma 0, fy at 0 comma 0, right? This is nothing but 0 comma 0, okay, because both these values were 0. Okay, so now for any u, thus for any small f user, for any unit vector u is equal to u1 u2 in R2, gradient of f at 0 comma 0 multiplied by dot product with u. What is this going to be? This is going to be 0 0 dot product with u1 u2. What will this become? This will become 0, not 0 comma 0, it's just 0. Okay, this will become 0 over here. Okay. Okay. So, but if u1 u2 is not equal to 0 comma no, sorry, if both u1 u2 u1 and u2 are non-zero, then this du f at 0 comma 0, okay, the numerator will be non-zero, no? Because your u1 and u2, see u1 square into u2, denominator is also going to be non-zero. u1 and u2 are both non-zero. Okay, so this is not equal to 0. Okay, but this gradient of f into u is 0. Okay, so in other words, that is the directional derivative of f along u, this is not equal to gradient of f dot u. Okay, so directional derivative does not satisfy this identity. Okay, the directional derivative of f over here does not satisfy this identity which we just proved in the previous theorem. Okay, so that means that the function is not differentiable. Okay, because if it is differentiable, it should have satisfied this identity here. Okay, hence not differentiable, because every differentiable function satisfies this identity. Okay, so that's about this problem. Okay, so see, the problem is that showing a function is differentiable or not differentiable involves showing a very complicated limit over there. That limit, the definition of differentiability, that limit of h comma q tends to 0 comma 0 of f of x plus, sorry, f of x plus h y plus k minus f of x y or x naught y naught, okay, minus alpha 1 h and minus alpha 2 k divided by root over that h square plus k square. This is a bit difficult definition to show because we may not know what is the value of alpha 1 and alpha 2. We know that it's going to be the partial derivative. Okay, even sometimes that may not be possible to find out the partial derivative in simple terms, but chalo, assume you found out that partial derivative in simple terms and all, and you can write down that x ratio over there which I just said. Problem is calculating that limit. Okay, because you're having a root over h square plus k square in the denominator. Okay, it might be difficult to simplify and get the value of that limit as 0. Okay, so that's why we have to try different other tricks like this one to show that the directional derivatives don't exist or something like that, and then conclude it is not differentiable. Right, obviously, yeah, this works only when you have a non-differentiable function. When you have a differentiable function, you still have to manually solve the limit and show that it is 0. Okay, this other tricks over here work only if the function is not differentiable. Okay, so that's all for this section. There are some more examples, but I can't do it right now. Okay. Yeah. So yeah. So what we'll do is yeah, we'll stop over here. We'll continue with the next subtopic on chain rule in the next class. Okay. Bye bye.